Right now, as you listen to these words, it feels as though time is carrying you forward. 1 second slips into the next. Thoughts arrive and disappear. Memories drift behind you, while possibilities wait somewhere ahead. Every instinct you possess tells you that existence is a river, flowing endlessly from past to future. Yet hidden inside the equations of modern physics is a possibility so strange that it unsettles even the scientists who study it. According to one of the deepest mathematical descriptions of reality ever discovered, this moment is not moving at all. The room around you appears stable. The sounds you hear arrive one after another. Your heartbeat marks a rhythm. Your breathing unfolds in sequence. Everything about ordinary experience suggests motion through time. But imagine for a moment that this sensation is not fundamental. Imagine that the passage of time is not a property of the universe itself, but something generated by the way consciousness encounters reality. Imagine that every moment of your life already exists, complete and unchanging, like pages resting quietly inside an infinite library. This idea is not science fiction. It emerges naturally from the work of Albert Einstein. In 1905, Einstein published the theory of special relativity, permanently changing humanity's understanding of space and time. Before Einstein, most people assumed that time flowed identically for everyone everywhere. A second on Earth was a second on Mars. A second for one observer was a second for all observers. Time was believed to be universal, a great invisible clock ticking behind the entire cosmos. Relativity shattered that assumption. Einstein demonstrated that measurements of time depend upon motion. Two observers moving relative to one another will not agree on the duration of events. Their clocks can tick at different rates. Their definitions of what is happening right now can differ. Something that appears simultaneous to one observer may not appear simultaneous to another. This was not merely a philosophical suggestion. It was a mathematical consequence of the structure of reality itself. A few years later, the mathematician Hermann Minkowski provided the geometric framework that revealed the full implications of Einstein's discovery. Space and time were no longer separate entities. They became aspects of a single four-dimensional structure called spacetime. 3 dimensions describe position, length, width, height. The 4th dimension describes time. Together they form the arena in which every event in the universe exists. Imagine drawing a map. Normally a map records locations in space. A city occupies one point. A mountain occupies another. Now imagine extending that map with an additional dimension representing time. Every event that has ever happened becomes a location inside a vast four-dimensional landscape. Your first day of school is there. Your 10th birthday is there. The moment you first fell in love is there. The moment you are listening to this video is there. Every experience becomes a coordinate inside space-time. The unsettling consequence is that nothing in Einstein's equations privileges the present moment. Physics contains no universal spotlight moving across space-time, announcing which event is happening now. The equations simply describe the entire structure. The past exists. The future exists. The present exists. All of them occupy different regions of the same four-dimensional reality. This perspective became known as the block universe. Picture a long film reel containing every frame of a movie. When projected onto a screen, the frames appear sequentially. Characters seem to move. Stories seem to unfold. Events seem to emerge from the future and disappear into the past. Yet inside the reel itself, every frame already exists. The ending is present just as surely as the beginning. Nothing inside the reel is becoming real. Everything is already there. The block universe proposes something similar about reality itself. Your life may not be a process of moments being created one after another. Instead, every moment may already exist within the larger structure of space-time. The child you once were is not gone. The elderly person you may someday become is not waiting to arrive. Both exist as different locations within the same cosmic architecture. This is difficult to accept because it contradicts direct experience. Human beings do not experience reality as a static structure. We experience it as movement. We remember the past. We anticipate the future. We feel ourselves traveling through time, yet the mathematics remain stubborn. Relativity offers no preferred present, no universal clock, no cosmic now, only the complete space-time manifold. Perhaps no statement captures the emotional weight of this idea more clearly than a letter Einstein wrote near the end of his life. In March of 1955, Einstein learned that his lifelong friend Michel Besso had died. Writing to Besso's family, Einstein attempted to offer comfort. But the comfort he offered was unusual. He wrote that for us believing physicists, the distinction between past, present, and future is only the meaning of an illusion, however persistent. The sentence has become famous because it reveals how deeply Einstein took the implications of his own theory. He was not speaking metaphorically. He was describing what the mathematics seemed to imply. If space-time is fundamentally a block, then death does not erase a person from reality. It merely identifies a different region of the structure. The moments in which someone lived remain part of space-time forever. Whether one finds this comforting or unsettling often depends on temperament. Some see permanence, others see imprisonment. But either way, the question remains: if the universe is a frozen four-dimensional structure, why does experience feel so dynamic? Why does consciousness encounter one moment after another? Why do we remember yesterday but not tomorrow? Why does time appear to flow? For decades, these questions lingered at the edges of physics. Many researchers accepted the block universe as a consequence of relativity, while quietly hoping that a deeper theory might eventually restore a more familiar picture of time. Then quantum mechanics entered the story, and instead of solving the mystery, it made it far stranger. During the 20th century, physicists developed a mathematical framework capable of describing atoms, particles, radiation, and the microscopic foundations of reality. Quantum mechanics became one of the most successful scientific theories ever created. Its predictions proved astonishingly accurate. Every modern computer, laser, transistor, and smartphone depends upon principles discovered through quantum theory. Yet quantum mechanics and relativity never fit together comfortably. One governs the very large, the other governs the very small. Physicists spent decades searching for a deeper framework capable of unifying both descriptions into a single theory. Eventually, that search produced an equation whose implications were even more radical than Einstein's, an equation that did not merely reinterpret time, an equation that seemed to erase time entirely. That equation would become known as the Wheeler-DeWitt equation, and its strange implications would lead some physicists to ask a question so profound that it continues to echo through cosmology today. What if time itself does not exist? As the night deepens and the stars continue their silent motion above Earth, hold that question gently in your mind. In the next chapter, we follow John Wheeler, Bryce DeWitt, and the search for quantum gravity into a place where clocks disappear, change becomes difficult to define, and the universe begins to resemble something far stranger than a flowing river of moments. Until then, rest comfortably. Let your thoughts drift among the stars, and if you enjoy these deep explorations into the mysteries of physics and existence, consider subscribing to Space Sleep Theory, where every journey begins with a question and ends somewhere beyond the edge of the known universe. Imagine standing inside a cathedral so large that its walls disappear beyond the horizon. Every pillar, every arch, every stone is perfectly still. There is no clock on the wall, no bell ringing in the distance, no sunrise or sunset beyond stained glass windows. Yet somehow, despite the complete absence of movement, you still possess the unmistakable feeling that time is passing. You remember a moment before this one. You anticipate a moment after it. The puzzle is not merely philosophical, it is mathematical. Because once physicists attempted to write down a quantum description of the entire universe, they discovered something deeply unsettling. The most fundamental equation they produced seemed to describe a reality in which time itself had vanished. When we perform ordinary physics, time is usually supplied from outside the system we are studying. A laboratory experiment unfolds over seconds or minutes. The clock on the wall tells us when measurements occur. A particle moves through space, while an external observer tracks its position as time advances. Even Schrödinger's famous equation assumes this arrangement. The wave function evolves because there is an independent time parameter against which change can be measured. The universe, however, creates a problem. There is no clock outside the universe. There is no observer standing beyond reality itself, holding a stopwatch and measuring cosmic evolution from an external perspective. The universe contains all clocks. It contains all observers. It contains every possible reference frame. Once physicists attempted to quantize the entire cosmos, the external time parameter disappeared. Nothing remained outside the system to serve as a universal clock. This is the heart of the problem that became known as the problem of time. The Wheeler-DeWitt equation appears deceptively simple. H hat psi equals 0. Yet hidden inside that compact expression is a profound challenge to our deepest intuitions. The equation does not describe a universe evolving through time. Instead, it describes a timeless quantum state containing every possible configuration of geometry and matter simultaneously. There is no universal ticking, no cosmic metronome, no master clock counting seconds since the Big Bang. To appreciate how strange this is, imagine opening a novel and discovering that every page exists at once. The beginning, middle, and ending are all present simultaneously. The characters do not move from one chapter to the next. The entire story simply exists as a complete object. From the perspective of someone holding the book, there is no flow. There is only structure. This is remarkably close to what the Wheeler-DeWitt equation seems to imply. Physicists did not arrive at this conclusion because they wanted to eliminate time. In fact, most found it deeply disturbing. The equation emerged naturally from the mathematics of combining quantum theory with general relativity. Time disappeared, not because anyone removed it deliberately, but because the equations themselves no longer required it. John Wheeler himself was fascinated by the implications. Throughout his career, he repeatedly returned to questions that bordered on philosophy. What is reality? What role does observation play? Why does the universe exist in the form we observe? Wheeler often pushed beyond the boundaries that many physicists felt comfortable exploring, yet even Wheeler struggled with the implications of a timeless universe. After all, if the fundamental equation contains no time, why do we experience time so vividly? Why do memories accumulate in one direction? Why do eggs break, but never spontaneously reassemble? Why does yesterday feel fixed, while tomorrow feels open? The equations seem to describe a frozen reality, yet our experience was one of constant motion. For decades, physicists searched for ways to recover time from a timeless foundation. One approach was to treat time as an emergent phenomenon rather than a fundamental one. Temperature provides a useful analogy. A single molecule does not possess a temperature. Temperature emerges only when vast numbers of particles interact statistically. Perhaps time works similarly. Perhaps the flow we experience emerges from deeper relationships hidden inside the timeless quantum state. This idea gained support through work by physicists such as Don Page and William Wooters in the 1980s. They proposed that time might arise from correlations between different parts of the universe. One subsystem could function as a clock relative to another subsystem. Nothing would evolve relative to the universe as a whole, but evolution could appear when one part was compared to another. Picture two dancers frozen in a photograph. The image itself does not move, yet their positions reveal a relationship. One dancer's posture provides information about the other's motion. In a similar way, a timeless universe might contain internal correlations that create the appearance of temporal flow. This concept remains an active area of research today, yet even if time emerges from correlations, the deeper question remains: what exactly is flowing? Consider your own life. You remember childhood. You remember conversations from years ago. You remember places you once visited. Those memories create a powerful sense that the past has receded behind you. But according to the block universe picture suggested by relativity, those moments have not vanished. They still exist as locations within space-time. The Wheeler-DeWitt equation appears to push the idea even further. Not only does the past continue to exist, the entire universe may exist as a single timeless structure. The flow, in that case, belongs not to reality itself, but to something about how conscious observers experience reality. This possibility unsettled many thinkers because it shifts the mystery rather than solving it. Instead of asking why time flows, we begin asking why we perceive flow within a timeless world. The distinction may sound subtle, but it changes everything. Imagine walking through an enormous art gallery containing every moment of your life displayed as individual paintings. One painting shows your first day at school. Another shows you watching this video. Another shows a distant future you have not yet experienced. The gallery itself does not change. The paintings remain fixed. Yet your awareness appears to move from one canvas to the next. The question becomes, what is this awareness that experiences succession inside a static structure? Physics provides partial answers. Neuroscience explains aspects of memory. Psychology studies perception. But the deeper mystery remains remarkably resistant to reduction. Why does consciousness experience a present moment at all? Why is awareness located here rather than elsewhere? Why does existence feel like an unfolding journey instead of a completed geometric object? These questions linger at the boundary between physics and philosophy, where equations alone cannot fully guide us, and it is here that another figure enters our story, a physicist who looked directly at the timeless implications of the Wheeler-DeWitt equation and decided to follow them wherever they led. His name was Julian Barbour. While many researchers searched for ways to restore time to physics, Barbour asked a different question entirely. What if the equation is correct exactly as written? What if time is not hidden? What if time is not emergent? What if time simply does not exist? The answer he arrived at would become one of the most radical visions ever proposed in modern science, a vision he called Platonia. And as we move into the next chapter, we will step into that strange landscape together, a realm where every possible moment exists simultaneously, where change is an illusion, and where the feeling of time itself may emerge from something far stranger than motion. Until then, allow your thoughts to drift gently through these questions. Let the equations settle quietly in the background, and if you enjoy exploring the deepest mysteries of physics, cosmology, and existence itself, consider subscribing to Space Sleep Theory. There is still a long journey ahead, and the strangest parts of the story are only just beginning. Imagine that somewhere beyond every galaxy, beyond every black hole, beyond even the fabric of space-time itself, there exists an infinite landscape containing every moment that could ever exist. Not every moment that does exist, every moment that could exist, every version of every life, every arrangement of every atom, every possible configuration of reality frozen into existence like photographs scattered across an endless plane. Somewhere within that unimaginable collection is the moment you are experiencing right now. Somewhere else is the moment when you were a child. Somewhere else is the final day of your life. Somewhere else are moments that never happen at all, alternate versions of events that never unfold in your history. According to Julian Barbour, one of the most radical thinkers in modern theoretical physics, this strange landscape may be closer to the truth than our ordinary understanding of time. Barbour did not begin by trying to create a philosophical theory. He began with the same equations that confronted every physicist working on quantum gravity. Like everyone else, he found himself staring at the Wheeler-DeWitt equation and its unsettling absence of time. But unlike many of his colleagues, he resisted the urge to repair the problem. He did not search for hidden clocks or emergent time variables. Instead, he asked a question that most physicists considered almost too dangerous to entertain. What if the equation is not missing time? What if reality itself is? The result was an idea he eventually called Platonia, named after Plato's ancient world of timeless forms. In Barber's vision, reality is not a movie unfolding frame by frame. Reality is the complete collection of all possible frames. There is no cosmic projector moving through them. There is no hidden mechanism advancing the story. There is only the collection itself. Every possible now exists. Every possible arrangement of the universe exists. What we call the passage of time emerges from relationships between these frozen moments, rather than from any actual flow. To understand how strange this proposal really is, picture an infinite library. Every book in the library contains a complete description of a single instant of reality. One book describes the universe exactly 1 second ago. Another describes the universe exactly 1 second from now. Another describes a universe where Napoleon won at Waterloo. Another describes a universe where the dinosaurs never disappeared. Another contains a version of your life that differs from this one by a single heartbeat. The library is infinite because the possible arrangements of matter and energy are unimaginably vast. Yet none of these books is being written. None is being read sequentially. They simply exist. Your experience of time, according to Barber, comes from finding yourself inside one particular kind of book. This is where the idea becomes even stranger. Most possible moments would not contain any evidence of a past. Imagine a completely random arrangement of atoms. It would not contain fossils. It would not contain memories. It would not contain photographs, tree rings, geological layers, written records, or neural structures encoding previous experiences. It would simply be a chaotic snapshot. Yet the moment you are experiencing right now is different. Your present contains countless traces of what appears to be a history. Your brain contains memories. Your surroundings contain evidence of causes and effects. Every object around you seems to tell a story about how it arrived here. Barber called such moments time capsules. A time capsule is a single frozen configuration of reality that contains within itself the appearance of a past. Importantly, according to Barber, the past does not actually need to exist. The present moment alone contains enough structure to create the impression that it does. Your memories are present structures inside your brain right now. The fossils in the ground are present structures right now. The light arriving from distant galaxies is present right now. Everything you regard as evidence for the past exists entirely within the current configuration of the universe. Think about what this means. Every memory you possess is a feature of the present. Every historical record is a feature of the present. Every photograph, every scar, every fossil, every ancient ruin exists only as part of the current arrangement of matter. We infer the existence of a past because these structures seem to point backward. But according to Barber, the only thing that truly exists is the present configuration itself. Imagine finding a novel lying on a table. The story appears to describe years of events. Characters grow older, relationships change, entire generations pass. Yet all of that history exists simultaneously within the pages of a single object. The story is not unfolding, it is simply there. In a similar way, Barber suggests that reality may consist of static moments whose internal structure creates the illusion of temporal depth. Naturally, this raises an immediate objection. If all moments exist equally, why do we experience one specific sequence rather than a random collection of disconnected snapshots? Barber's answer is subtle. Certain moments are linked by extraordinary structural similarities. A moment containing a memory of childhood tends to resemble another moment containing that childhood itself. Configurations cluster together. They form chains of consistency. To an observer embedded within one of these configurations, the chain appears as a continuous history. Yet from the outside perspective of Platonia, no actual movement occurs. There are only relationships among static states. This idea feels almost impossible to accept because every instinct we possess tells us that time flows. You woke up this morning, you watched hours pass, you moved through space, your thoughts changed from one moment to the next. The flow seems undeniable, but relativity already challenged similar intuitions. For most of human history, it seemed obvious that time passed at the same rate everywhere. Einstein showed otherwise. It seemed obvious that simultaneity was universal. Einstein showed otherwise. Barber argues that our intuition regarding temporal flow may be equally misleading. The deeper question becomes whether the feeling of motion requires motion at all. Consider a flip book. Each page is static. Nothing moves on any individual page. Yet when the pages are viewed in sequence, motion appears. The traditional understanding of time assumes there must be a hand flipping the pages. Barber removes the hand entirely. The pages simply exist. The apparent motion arises from the structure of the pages themselves. Many physicists remain skeptical of this conclusion. Some argue that it merely relocates the mystery rather than solving it. Others point out that modern physics often relies on dynamical laws that seem difficult to formulate without time. Yet even critics acknowledge something remarkable. The timelessness Barber embraces is not invented arbitrarily. It emerges naturally from some of our deepest physical theories, and perhaps that is what makes the idea so unsettling. We often assume that time is among the most fundamental features of existence, more fundamental than matter, more fundamental than life, more fundamental than consciousness. Yet the closer physics moves toward a description of ultimate reality, the more time begins to resemble something secondary, something emergent, something that may not exist in the way we imagine. If Platonia is even partially correct, then the universe is far stranger than the block universe of Einstein. In Einstein's picture, every moment exists within a four-dimensional space-time. In Barber's picture, even space-time itself becomes secondary. What ultimately exists is a timeless landscape of possible configurations. Space emerges, time emerges, history emerges, the flow of experience emerges. But beneath all of it lies a silent realm where nothing moves because movement itself is not fundamental, yet an even deeper mystery remains unresolved. If all moments exist equally, why do some contain an arrow of time? Why do memories point toward the past rather than the future? Why does entropy increase in one direction? Why does the universe seem organized around a distinction between before and after? To answer those questions, we must leave Platonia for a moment and turn toward one of the most improbable facts in all of physics. A number so astonishing that Roger Penrose once compared it to a target smaller than anything human intuition can comprehend. A number that may hold the key to why time appears to flow at all. And as we move into the next chapter, we will discover that the greatest mystery about time may not be why it exists, but why the universe began in precisely the condition required to make time seem real. For now, allow your mind to rest within the strange stillness of Platonia. Imagine every moment of your life existing simultaneously, suspended in a vast, timeless landscape. And if you enjoy these deep journeys into physics, cosmology, and the nature of reality, consider subscribing to Space Sleep Theory. There is much further to travel, and the deepest puzzles are still waiting ahead. Imagine waking up tomorrow morning and discovering a deck of cards lying on your kitchen table. Every card is perfectly arranged, not merely by suit, not merely by color, but in exact numerical order from ace through king, with every suit grouped flawlessly. You would not assume the deck had been shuffled randomly and happened to land that way. The arrangement is simply too specific. Now imagine repeating the experiment with 1,000 decks, then 1,000,000, then every deck that could ever exist across every planet in every galaxy. Even then, the odds remain overwhelmingly against such perfect order appearing by accident. Yet according to modern physics, the early universe was arranged with a level of order so extraordinary that even this analogy barely scratches the surface. As we left the previous chapter, we arrived at a profound mystery. If time may not be fundamental, why does it appear to move in a particular direction? Why do we remember yesterday, but not tomorrow? Why does cream mix into coffee but never separate itself back out? Why do stars burn their fuel, galaxies evolve, civilizations rise and fall, and every living thing move from birth toward death rather than the reverse? The answer, according to modern physics, is entropy. Entropy is one of the most misunderstood concepts in science. It is often described as disorder, but that simplification can be misleading. A better way to think about entropy is as the number of possible microscopic arrangements corresponding to a particular macroscopic state. A shattered glass has vastly more possible configurations than an intact glass. A room full of mixed air molecules has vastly more configurations than a room where every molecule sits neatly in one corner. Systems naturally evolve towards states that can be realized in more ways because those states are statistically overwhelming. This tendency is formalized in the second law of thermodynamics, one of the most reliable principles ever discovered. In an isolated system, entropy tends to increase. Ice melts, buildings decay, stars exhaust their fuel. The universe moves from lower entropy states toward higher entropy states. Yet hidden within this familiar law lies a staggering question. If entropy always increases, then the universe must once have possessed lower entropy than it does today. And if we follow that logic backward far enough, we arrive at one of the most astonishing discoveries in cosmology. The early universe was not merely lower in entropy. It was fantastically, almost impossibly, lower in entropy. This realization emerged most forcefully through the work of Roger Penrose. During the late 20th century, Penrose began examining the initial conditions of the Big Bang. Physicists already knew the early universe was extremely hot, extremely dense, and remarkably smooth. At first glance, smoothness might seem like a high entropy condition. Gas spreading evenly through a room generally corresponds to maximum entropy. But gravity changes everything. Gravity prefers clumping, given enough time. Matter under the influence of gravity tends to collapse into increasingly structured configurations. Stars form, galaxies form, black holes form, and black holes, as physicists eventually realized through the work of Jacob Bekenstein and Stephen Hawking, possess enormous entropy. This means that a perfectly smooth universe is actually a state of extraordinarily low gravitational entropy. The Big Bang was not a complete, random, chaotic explosion. It was a breathtakingly ordered beginning. Penrose attempted to quantify just how special this beginning was. His estimate became one of the most famous numbers in theoretical physics. He calculated that the phase space volume corresponding to our universe's initial low entropy condition represented roughly 1 part in 10, raised to the power of 10, raised to the power of 123. Even writing the number feels absurd. 10 circumflex, 123. There are not enough particles in the observable universe to write out all its zeros. There are not enough atoms in all known galaxies to represent it physically. The number lies so far beyond ordinary comprehension that analogies begin to fail. Imagine covering every particle in the observable universe with its own separate universe filled with particles, then covering every particle in all of those universes with another universe. Continue building towers of universes upon universes until language itself begins to collapse under the weight of the scale involved. You would still not approach the improbability Penrose was describing. What exactly does this mean? It means that among all the possible ways the universe could have begun, the initial state that actually occurred occupies an unimaginably tiny region of possibility space. The universe appears to have started in a condition so special that many physicists regard it as the deepest unsolved problem in cosmology. And this brings us directly back to the mystery of time, because the arrow of time is not something imposed on the universe from outside. It emerges from this low entropy beginning. If the universe had started in thermal equilibrium, with maximum entropy already achieved, there would be no meaningful distinction between past and future, no evolution, no complexity, no stars, no biology, no observers wondering about existence. The flow of time depends on the fact that entropy began astonishingly low. Imagine a ball resting high on a mountain peak. Gravity naturally carries it downward. The motion feels directional because the ball begins in an unlikely position. If the ball already rested at the bottom of the valley, there would be nowhere further to go. Similarly, the universe appears to be rolling downhill through entropy. The reason time possesses a direction is that the cosmos began perched on an extraordinarily improbable summit, yet this answer only pushes the mystery one level deeper. Why was the ball placed on the mountaintop in the first place? Why did the universe begin in such an exceptional state? For decades, physicists have struggled with this question. Some hoped inflation would provide the answer. Inflation, proposed by Alan Guth in 1981 and later refined by André Linde and others, describes a brief period of exponential expansion shortly after the Big Bang. Inflation successfully explains many observed features of the cosmos. It accounts for the large-scale smoothness of the universe. It explains why distant regions share similar properties despite appearing causally disconnected. But inflation itself requires special initial conditions. The problem does not disappear, it moves. Roger Penrose became one of inflation's most vocal critics on precisely these grounds. He argued that inflation presupposes the very low entropy conditions it is often claimed to explain. The universe must already occupy a remarkably special state for inflation to begin. The mountain remains. The ball still requires placement. And so the mystery survives. As cosmologists pushed deeper into these questions, some began exploring even more radical possibilities. Perhaps our universe is only one among countless universes. Perhaps every possible set of physical constants exists somewhere within an immense multiverse. If enough universes exist, then highly ordered beginnings become inevitable somewhere. This idea gained popularity because it appears to soften the force of fine-tuning arguments. If there are enough cosmic lottery tickets, eventually someone wins. Yet the multiverse introduces its own difficulties. How many universes exist? What generates them? What determines the laws governing the larger ensemble? Why does the multiverse itself possess the structure required to produce universes at all? Each answer seems to generate new questions. The regress continues, and throughout all of this, the original mystery remains strangely untouched. Why does reality possess an arrow of time? Why does existence feel like a journey unfolding from past toward future? Why does consciousness find itself embedded within a universe that began in such an extraordinarily special condition? Julian Barber would eventually offer a remarkable alternative perspective through a concept known as the Janus point. Rather than viewing entropy as increasing from a single beginning, he proposed that the universe might contain a central point from which entropy increases in two opposite directions simultaneously. In such a picture, observers on either side would each perceive themselves as moving away from a low entropy past. It is one of the strangest ideas ever proposed about time, and it may offer a radically different way of understanding the origin of the arrow itself. As we move into the next chapter, we will follow that possibility into territory where the distinction between past and future becomes increasingly fragile, where the universe may possess two futures and two pasts depending on where one stands, and where the familiar flow of time begins to resemble something even stranger than an illusion. For now, allow your thoughts to settle gently upon the immense improbability of the cosmos. Consider the extraordinary fact that every memory you possess, every star in the night sky, every moment of awareness exists because the universe began in a state so special that physics still struggles to explain it. And if you enjoy these slow explorations into the deepest mysteries of reality, consider subscribing to Space Sleep Theory. There is still much further to travel, and the strangest landscapes of all are waiting just ahead. Universe with two futures. Imagine standing on the peak of a vast mountain, unlike any mountain that exists on Earth. From the summit, two valleys stretch away in opposite directions. Rivers flow down both sides. Winds move outward from the center. Every path leads away from where you stand. If you begin walking east, it seems obvious that the mountain lies in your past and the valley ahead lies in your future. But someone walking west experiences exactly the same thing. They also see the mountain behind them and the valley ahead of them. Both travelers believe they are moving forward in time. Both are correct. The mountain is not the beginning of one journey. It is the center of two. This image captures one of the most fascinating attempts to explain the arrow of time without assuming a special beginning. It emerged from the work of Julian Barber, Tim Kozlowski, and Flavio Mercati during the early 21st century. Their proposal, known as the Janus point model, takes its name from Janus, the Roman god depicted with two faces looking in opposite directions. One face gazes toward the past, the other gazes toward the future, yet both belong to the same being. The Janus point begins with a simple observation. Nearly every discussion of entropy assumes that the universe started in an extraordinarily low entropy state. The problem, as we explored in the previous chapter, is that such a beginning appears almost impossibly special. Roger Penrose's calculations suggest that the initial conditions occupy an unimaginably tiny region of possibility space. Physicists have spent decades trying to explain why the universe began in precisely that configuration. Barber's response was to ask whether the problem itself might be framed incorrectly. What if the universe did not begin in a low entropy state? What if the low entropy condition was not a beginning at all? What if it was a middle? To understand this idea, imagine a cloud of particles floating freely through space under the influence of gravity. At first, the particles move closer together. The cloud contracts. Eventually, it reaches a state of maximum compression. Then it begins expanding again. To an observer watching from one side of that turning point, the expansion appears to define the future. To an observer on the other side, expansion also appears to define the future. Both observers see entropy increasing. Both experience a thermodynamic arrow of time pointing away from the central state. The remarkable feature of the Janus point is that it generates two arrows of time naturally. Time does not emerge because the universe began in an extraordinarily ordered condition. Instead, order appears at a central point, from which disorder increases in both directions. Imagine dropping a stone into a still pond. Ripples move outward in every direction. No ripple experiences itself as moving away from the center because it knows where the center is. It experiences movement because the surrounding pattern changes. In a similar way, observers embedded within the universe experience a direction of time because complexity increases as they move away from the Janus point. This idea immediately sounds bizarre because we instinctively think of the past as fixed and unique. Yet physics itself does not always share that intuition. The fundamental equations governing particles are, in many cases, time-symmetric. Run the equations forward or backward, and they remain valid. Newton's laws work both ways. Maxwell's equations work both ways. Even much of quantum mechanics remains symmetric under time reversal. The great exception is entropy. Entropy is what creates the distinction between past and future. Entropy is what gives time its apparent direction. And if entropy can increase away from a central point in two directions simultaneously, then two opposite futures become possible. Imagine living on one side of the Janus point. Every memory you possess points toward the central state. Every fossil, every ancient star, every record of cosmic history leads backward toward what appears to be the beginning. Yet according to the model, another civilization could exist on the opposite side. Their memories also point toward the same central state. Their history books describe a past leading toward it. Their entropy increases away from it. To them, their future extends in the opposite direction from ours. Neither civilization experiences itself as moving backward. Both experience normal time. Both perceive themselves as moving from past to future. The distinction exists only from a perspective outside both histories. This is one reason the Janus point attracts so much interest. It transforms the arrow of time from a fundamental feature of reality into a local perspective emerging from the large-scale structure of the universe. Yet the idea remains controversial. One reason is that it challenges one of our deepest assumptions. We naturally imagine that the universe must have a beginning. Every story begins somewhere. Every life begins somewhere. Every journey begins somewhere. Cosmology itself often describes the Big Bang as the ultimate beginning. The Janus point invites us to imagine something different, not a beginning, a center, not the first moment, a moment of maximum simplicity, from which complexity emerges in both directions. To appreciate how radical this is, picture opening a novel exactly in the middle. On the pages ahead, characters age, relationships evolve, civilizations rise and fall. On the pages behind, the same thing happens. If you started reading outward from the center in either direction, both halves would appear to possess a past and a future. The structure of the story itself would create the arrow. This possibility becomes even more intriguing when combined with the timeless ideas we explored earlier. Remember Platonia, remember the landscape of all possible nows. In Barber's framework, the Janus point does not necessarily require time to exist fundamentally. Instead, the arrow emerges from relationships among configurations. Certain regions of configuration space naturally exhibit increasing complexity away from points of minimal complexity. Observers embedded within those regions experience temporal flow, even though the deeper reality remains timeless. In this sense, the Janus point serves as a bridge between two puzzles. It helps explain why time appears directional, and it helps explain why the universe seems to have begun in an extraordinarily ordered state. Whether the model ultimately proves correct remains uncertain. Modern cosmology has not reached a consensus. Observational evidence remains incomplete. Competing theories continue to be developed, yet the importance of the idea lies not merely in whether it succeeds. Its importance lies in demonstrating how profoundly our assumptions about time can be challenged, because once we begin questioning the arrow of time, other mysteries emerge. What exactly is a memory? Why do certain physical structures preserve information about the past? Why does consciousness experience a continuous stream rather than isolated moments? And perhaps most importantly, if time is not fundamental, what is the true relationship between observer and reality? These questions lead us toward territory where physics, information, and consciousness begin to overlap in increasingly unexpected ways. The next chapter will take us deeper into that landscape. We will explore how memory itself may be connected to the structure of reality, why observers occupy such a peculiar position in modern physics, and why some researchers believe the experience of temporal flow may reveal something profound about the nature of existence itself. For now, allow yourself to linger for a moment on the image of the mountain with two valleys stretching into opposite horizons. Imagine civilizations on both sides, each convinced they are moving forward through time, each watching entropy increase, each carrying memories that point toward the same distant center. It is a strange picture, but then again, so much of modern physics has turned out to be stranger than common sense ever anticipated. And if you enjoy these slow journeys through the deepest questions of cosmology and reality, consider subscribing to Space Sleep Theory. There is still a long path ahead, and some of the most fascinating mysteries are only now beginning to appear on the horizon. If the Janus point gives time a center instead of a beginning, then the next question becomes unavoidable. Why does it feel as if we are moving away from that center in a single direction, carrying the past behind us and the future ahead? The answer proposed by Julian Barber does not rely on motion through time at all. It begins instead with something more subtle, something embedded directly in the structure of each moment of the universe. He calls them time capsules. A time capsule is not a physical object in the ordinary sense. It is not a container buried in the ground, waiting to be opened by some future civilization. It is a configuration of the universe, a particular arrangement of matter in which traces of other configurations appear to be encoded. Rocks contain fossils, ice cores contain trapped atmospheric gases, starlight carries information about distant events, and most importantly, brains contain what we call memories. In Barber's framework, all of these structures exist not because they were produced in a past that no longer exists, but because they are features of a single present configuration. There is no flow of time carrying information from one moment to another. There is only a vast landscape of possible configurations, and some of those configurations happen to contain internal correlations that resemble what we interpret as history. To understand how radical this is, it helps to slow the idea down and examine what is actually being claimed. In everyday thinking, a photograph exists because light once reflected off a real scene and struck a sensor or chemical surface. That event is assumed to belong to the past, and the photograph is treated as a physical remnant of something that happened earlier. Cause precedes effect. History leaves traces, but in the timeless view Barber is exploring, there is no earlier moment in which the photograph was created. There is only a single configuration of the universe in which the photograph exists, alongside everything else. The correlation between the image and what we interpret as its source is not produced by a historical process. It is simply part of the structure of that configuration. The same reasoning applies to memory. A memory, in this picture, is not a surviving imprint of a past experience. It is a present physical state of a brain, a highly organized pattern of neurons and synapses that encodes information consistent with a particular narrative. That narrative feels like something that happened, but the feeling itself is also part of the configuration. Nothing in the equations requires that the event being remembered exists in a separate past. What exists instead is a single structure in which the brain, the environment, and the records within it all align in a mutually consistent way. This is what makes time capsules so central to the entire discussion. They are the mechanism through which a static universe can generate the appearance of history. At first, this may sound like a philosophical trick, as if explanation has been replaced with reinterpretation, but Barber's argument becomes sharper when placed alongside the Wheeler-DeWitt equation from quantum gravity. That equation, as we saw earlier, does not contain time as a fundamental variable. It describes a universal wave function defined over all possible configurations of space and matter, but it does not evolve. Instead of describing change, it assigns structure, and within that structure, some configurations are vastly more common than others. Barber's key suggestion is that configurations containing time capsules are not rare accidents. They may be statistically favored. The wave function of the universe, even if static, may have a distribution that strongly weights configurations in which internal records align consistently. In such a case, most observers would inevitably find themselves embedded in configurations that look like they have a past. From the inside, this produces a powerful illusion. From the outside, there is no illusion at all, because there is no outside perspective in time. There is only the configuration itself. This is where the idea becomes unsettling in a more precise way. It does not simply deny that time flows. It suggests that the structure responsible for the appearance of flow is intrinsic to each moment, rather than a relationship between moments. The implication is that every detail of what you call your past, your childhood, your earlier experiences, the origin of the Earth, the formation of galaxies, is not something preserved from another time. It is something reconstructed from patterns present right now. But reconstruction here does not mean fabrication. It means consistency. The brain is not inventing an arbitrary story. It is embedded in a configuration where multiple independent traces, geological, biological, astronomical, all point toward a single coherent narrative. The strength of time capsules lies in this redundancy. Different systems all encode compatible information. Rocks agree with ice cores. Ice cores agree with starlight. Starlight agrees with memory. The agreement creates what we interpret as history. The deeper claim is that no actual history is required for this agreement to exist. To make this more intuitive, imagine a single frame of a film so detailed that it contains within it all the information needed to reconstruct an entire storyline. You see wear on clothing, objects arranged in specific ways, expressions on faces, environmental conditions all pointing toward prior causes. Now imagine there is no film. There is only that one frame. The story is not something that happened before the frame. The story is something that exists as an interpretation of the structure inside the frame itself. Barber's claim is that the universe may be like this, but at a vastly more complex level. Once this idea is in place, the connection to entropy becomes unavoidable. The reason time capsules are so compelling is that they appear to encode a direction. They always seem to point toward lower entropy states in what we call the past. Fossils indicate simpler biological forms. Cosmic background radiation indicates a smoother early universe. Memories point toward earlier, more ordered brain states. But if there is no real temporal sequence, then entropy increase is not a process unfolding through time. It is a gradient across configuration space. Some regions of that space contain more structure than others, and observers necessarily find themselves in regions where structure allows for self-consistent narratives. This is where the idea begins to connect with the Janus point again. If there is a central region of minimal complexity, then configurations on either side naturally exhibit increasing complexity away from it. Time capsules would then not just be random features of configuration space, but systematic ones, emerging wherever complexity gradients support internal consistency. In that sense, memory is not a window into the past. It is a feature of how certain regions of reality organize information, and once memory is reinterpreted this way, the boundary between observer and universe begins to blur. The brain is no longer a passive recorder of time. It is part of the structure that defines what time appears to be. This sets the stage for the next step in the argument. Because if memories are just structural features of static configurations, then the next question becomes even more pressing. Why do these configurations feel like they are being experienced from within? Why is there an inside at all? In the next chapter, we move from the structure of time capsules to the question of observation itself. We will examine why physics seems to require observers in a way that is more fundamental than it first appears, and why the act of experiencing a moment may be more deeply tied to the structure of reality than any motion through time. And with that, the landscape begins to shift again, away from memory and toward consciousness itself. If time capsules explain why the past appears to exist, then something deeper still is needed to explain why there is anything that appears at all. Because embedded inside every time capsule is not just structure, but an observer interpreting that structure, a brain that reads fossils as history, a mind that experiences continuity, a system that does not merely contain information, but organizes it into the feeling of a world. And once you start asking what an observer actually is in a universe like this, the question becomes much less straightforward than it first appears. In classical physics, an observer is simply something that records data. A thermometer reads temperature. A telescope records light. A brain records experiences. The observer is not fundamentally different from the system being observed. It is just another physical object, governed by the same laws, but in the frameworks we have been exploring, especially those where time itself is not fundamental, this separation begins to blur. If the universe is described by a static configuration space, whether in Barber's Platonia or in the Wheeler-DeWitt formalism, then an observer is not someone who moves through time collecting information. An observer is a pattern within a single configuration that contains within it a self-consistent structure of recorded information. This changes the role of observation from an external act to an internal feature of the universe. To see what this means, imagine once again a single configuration of the universe, frozen in the sense that nothing evolves outside it. Within that configuration exists a brain. That brain contains memories, sensory structures, predictive models, and internal correlations that all align in a coherent way. From the inside of that brain, there is an experience of flow. There is a sense of before and after. There is a feeling of being located at a particular point in time. But from the outside perspective of the configuration itself, nothing is happening. There is no transition from one state to another. There is only the structure that gives rise to the experience of transition. This is where the concept of information becomes central. In modern physics, especially in quantum theory and quantum gravity, information is not just a metaphor. It is a physical quantity. It can be quantified, conserved, entangled, and distributed across systems in ways that defy classical intuition. But in a timeless framework, information is not something that is transmitted through time. It is something that is encoded in relationships within a single structure. A memory, in this sense, is not information traveling from past to present. It is a correlation between different parts of a configuration that produces the internal model of a past. This leads to a subtle but profound shift in how observers are understood. An observer is not defined by what it sees at a moment. It is defined by the internal consistency of the information it contains. A conscious system is one in which information is organized in such a way that it generates a coherent model of the universe, including a model of itself within that universe. From this perspective, consciousness is not an external addition to physics. It is a pattern of organization within physical structure. But unlike classical patterns, it is a pattern that refers to itself. This self-referential structure is what produces the feeling of being inside a world. At this point, it becomes tempting to ask whether consciousness is doing something more than just organizing information. Some interpretations of quantum mechanics have suggested that observation plays a fundamental role in defining physical reality itself. Others argue that consciousness collapses probability distributions into definite outcomes. These ideas remain controversial, and most physicists prefer interpretations that do not give consciousness a special physical role. But even without invoking quantum measurement in a mystical sense, there remains a deep question about why physical systems give rise to subjective experience at all. In a timeless universe, this question becomes even sharper because there is no flow generating experience step by step. There is only structure, and yet within that structure, there is something it feels like to be a part of it. One way to approach this is to focus on prediction. A brain is not just a passive recorder of information. It is an active, model-building system. It continuously generates expectations about sensory input and updates itself based on discrepancies. This predictive structure is deeply tied to how neuroscientists understand perception today. The brain constructs a model of reality, and what we experience is that model, not raw data. In a timeless framework, this predictive activity is not happening over time in a fundamental sense. It is encoded as a pattern within a configuration that contains both the model and the data it is consistent with. The sense of update, of change, of anticipation is part of the structure itself. This suggests that the feeling of temporal flow may arise from the internal architecture of self-referential systems. A system that contains a model of its own future states will necessarily contain structures that represent transition, even if no transition exists externally. The experience of movement through time may be the way a static system encodes relationships between different internal states of itself. This idea connects naturally back to time capsules. A brain that contains memories is already a system that encodes relations between different configurations. It encodes earlier states as internal representations. If it also encodes predictions, then it contains a bidirectional structure, a mapping from past-like states and future-like states, both embedded within the same physical organization. From the inside, this looks like flow. From the outside, It is simply structure. At this point, it becomes clear that observers are not separate from the physics they observe. They are part of the configuration space itself. They are regions where information is organized in such a way that the universe becomes internally describable from within. And this leads to a surprising consequence. If observers are just patterns in configuration space, then the existence of a universe that can be observed is not a separate problem from the existence of the universe itself. The two are linked. A universe without observers would still be a configuration space, but it would contain no structures capable of constructing internal models. A universe with observers is one in which the structure supports self-referential information loops. This raises a final question for this chapter. Why does the universe allow for such structures at all? Why does configuration space contain regions where information becomes self-modeling, recursive, and stable enough to generate the experience of continuity? Some would say this is a consequence of physical law. Others would say it is a selection effect. We find ourselves in such regions because only such regions can be observed. Others still suggest it points toward deeper principles not yet understood, where information, physics, and consciousness are not separate categories, but different expressions of the same underlying structure. Whatever the answer, the direction of thought is becoming clear. The more deeply we examine time, the more it dissolves into relationships. The more we examine observers, the more they dissolve into structure. And the more we examine structure itself, the more it begins to resemble something that is not static in the ordinary sense, but self-organizing in a way that gives rise to experience. In the next chapter, we will turn toward that final layer of structure, information itself. We will explore whether the universe is best understood not as matter in motion, but as relationships of information across configuration space, and whether reality at its deepest level is fundamentally computational in nature. And if that is the case, then the question of time may have been the wrong question all along. If observers are patterns within configuration space, and time is not a flowing background, but something that emerges from relationships, then there is one concept that begins to sit underneath everything else: information. Not information in the casual sense of messages or signals, but information in the precise physical sense used in modern physics and mathematics: correlations, constraints, structure, the way one part of a system limits or defines another. In the frameworks we have been exploring, from relativity to quantum gravity to Barber's Platonia, the language of information keeps appearing in different forms. Entropy is information about microscopic configurations. Quantum states encode probabilities, which are themselves structured information. Even space-time geometry, in general relativity, is a way of encoding how distances and causal relationships constrain possible events. So a natural question emerges: if time dissolves at the fundamental level, and if observers are just structured patterns, what remains as the most basic description of reality? One answer increasingly suggested in theoretical physics is that the most fundamental layer is not matter, not space-time, and not even fields in the traditional sense, but information itself. To see what this means, imagine once again the idea of Platonia, the space of all possible configurations of the universe. Each point in this space is a complete description of a possible reality. A universe is not something that evolves through time. It is a point, or a structured region, within this vast landscape. Now imagine that instead of thinking about what physically exists inside each configuration, we think about how each configuration relates to every other configuration. Some configurations are similar, some are radically different, some can be transformed into others through smooth changes in geometry or matter distribution. Others are separated by enormous structural distance. What begins to matter is not the individual configurations themselves, but the network of relationships between them. This is where information enters the picture in a deeper way. Information is not just what is contained in a state, it is what distinguishes one state from another, and how that distinction can be measured, compressed, or predicted. In thermodynamics, entropy is defined in terms of the number of microscopic configurations compatible with a macroscopic state. In quantum theory, entanglement measures how information is distributed across subsystems. In both cases, the central idea is the same. What matters is not the objects themselves, but the structure of possibilities. If we extend this viewpoint to the entire universe, then Platonia itself becomes an information space. Each point is not just a universe, but a bundle of relationships encoded in a specific way. The geometry of Platonia, the action that defines its structure, and the measure that weights its configurations can all be interpreted as statements about how information is organized at the deepest level. This leads to a provocative reinterpretation of physics. The laws of nature are no longer simply rules governing how matter behaves. They become constraints on how information can be arranged consistently. In this view, the Wheeler-DeWitt equation is not just a statement that the universe does not evolve in time. It is a statement about the global structure of information. The wave function of the universe encodes all possible informational configurations simultaneously, and the equation imposes consistency conditions on that total structure. Similarly, entropy is no longer just a measure of disorder. It becomes a measure of informational accessibility. Low entropy states are those in which information is highly constrained and structured. High entropy states are those in which information is dispersed across many microscopic possibilities. This reframing is powerful because it unifies many of the ideas we have already encountered. Time capsules are informational structures that encode consistent histories. Observers are systems that process and integrate information in self-referential ways. The Janus point is a feature of configuration space where informational complexity is minimized and then increases in both directions. Even the arrow of time can be reinterpreted in informational terms. The apparent flow from past to future is not a movement of physical states through time, but a progression from states of lower informational accessibility to higher dispersal. Memory, in this sense, is not a trace of the past. It is a stable informational structure that persists within a larger space of possibilities. Once this shift is made, something subtle happens. The distinction between physics and computation begins to blur. A computational system is defined by rules that transform information from one state to another. If the universe is fundamentally informational, then its evolution, or its timeless structure, can be described as a kind of computation. But unlike ordinary computation, there is no external clock driving steps forward. The computation is embedded in the structure itself. This idea appears in several areas of modern theoretical research. In digital physics, some researchers suggest that space-time and matter emerge from underlying informational networks. In quantum information theory, space-time geometry has been linked to entanglement patterns. In certain approaches to quantum gravity, geometry itself is reconstructed from informational relations rather than assumed as a background. What unifies these ideas is the suggestion that information is not something that exists inside the universe. Instead, the universe is something that exists as information. From this perspective, Platonia is not just a space of possible universes. It is a complete informational structure containing all possible relational configurations. Time does not exist as a fundamental axis within this structure. Instead, what we interpret as time is the way information is organized along paths of increasing or decreasing correlation. This has a profound implication for the idea of change. Change, in the ordinary sense, implies that something becomes something else. But, in an informational framework, there is only variation across structure. There is no external timeline against which change is measured. There are only patterns that encode relations between different informational states. Even the idea of causality begins to shift. Cause and effect are no longer temporal sequences. They become constraints within the informational structure. One configuration is related to another not because it comes before it, but because the structure of the whole requires consistency between them. At this stage, it becomes tempting to ask whether this informational picture is just a reformulation of physics or something deeper. Is it merely a different language for describing the same equations, or does it point toward a genuinely new ontology? The answer is not settled. Many physicists treat information as a useful tool rather than a fundamental substance. Others suspect that it may be the most accurate description we currently have of what reality is at its core. But regardless of interpretation, one thing becomes clear. As we move deeper into modern physics, from relativity to quantum gravity to cosmology, the traditional categories begin to dissolve. Space becomes geometry. Geometry becomes relation. Relation becomes information. And information begins to look less like a description of reality and more like reality itself. In the next chapter, we will step beyond information and return to the question that has been hovering in the background since the beginning. If time, space, matter, and even observers can all be reinterpreted as structures within a deeper informational framework, then what does it mean for anything to exist at all? And more importantly, why does this structure exist rather than nothing? Once time is removed as a fundamental ingredient, something unusual happens to the question of existence itself. The familiar picture of a universe beginning at a moment and unfolding through time stops being available. There is no first instant in which reality switches from non-being to being. There is no cosmic starting point where existence is switched on like a light. Instead, what remains is structure, whether we describe it as space-time, or Platonia, or a wave function over configurations, or an informational network of relations. The underlying object in all of these pictures is not something that happens. It is something that is, and that immediately forces a question that physics does not usually answer directly. Why this structure, rather than none at all? In everyday reasoning, we are used to explanations that operate within a system. If a glass breaks, we look for a cause inside the world, a hand, a force, a collision. If a planet moves, we look for gravitational interaction. Even in cosmology, when we ask why galaxies form or why entropy increases, we are still operating inside an assumed framework of laws, fields, and space. But when we ask why there is a framework at all, the usual style of explanation begins to run out of ground to stand on. This is where the idea of Platonia becomes especially revealing. Platonia, in Barber's formulation, is not a universe evolving in time. It is the total space of possible configurations, each one a complete description of a possible cosmos. It is not something that happens. It is something that simply exists as a mathematical structure. If one adopts this view seriously, then reality is not a process, but a totality. Every possible configuration is already present in the structure. What we call experience is simply being located within one of those configurations. At first glance, this seems to dissolve the need for a beginning. If all configurations exist timelessly, then nothing needs to be created. There is no transition from nothing to something, because there was never a before in which nothing existed. But the deeper question remains untouched. Why is there a Platonia at all? One possible answer is to say that Platonia exists necessarily, that its structure is logically unavoidable, the only possible mathematical object of its kind. But this claim is extremely strong, and there is no consensus in mathematics or physics that it is true. The space of mathematically consistent structures appears vast, not singular. Different choices of symmetry, action, or constraint produce different configuration spaces, each internally coherent. So necessity is not something we can assume without argument. Another answer is to say that Platonia is a brute fact. It simply exists, and no further explanation is possible or required. At this point, explanation itself is declared to stop. The structure is what it is, and the question of why it is that way is treated as meaningless. But this move comes at a cost. It is not an explanation so much as a refusal of explanation. And more importantly, it is not a move unique to any one worldview. The same strategy could be applied to any fundamental entity, whether it is a universe, a multiverse, a wave function, or a law of physics. At some point, every chain of explanation can be halted by declaring its foundation to be self-sufficient, which means the brute fact move does not resolve the question, it only relocates it. There is a third possibility, one that appears in different forms across philosophy and theology. It is the idea that the structure of reality is contingent, and therefore depends on something beyond itself, something that is not part of Platonia, not part of space-time, not part of any physical or mathematical description we can write down. At this point, physics reaches its boundary. The tools we use to describe structure, equations, symmetries, configuration spaces, informational relations, all of them presuppose a domain in which they apply. They describe relationships within reality, not the source of reality itself. This is why the question, why is there something rather than nothing, resists being absorbed into physics. Physics, by definition, describes what exists under certain rules. It does not normally describe why those rules, or anything at all, exist in the first place. And yet, as we have seen throughout this exploration, modern theoretical physics keeps pushing us toward descriptions of reality that are increasingly abstract, increasingly timeless, and increasingly structural. The universe becomes a geometry. The geometry becomes a space of possibilities. The space of possibilities becomes an informational network. And at each step, the intuition that reality is a process unfolding in time becomes weaker. What remains is a deeply ordered structure that is astonishingly specific. The laws are not arbitrary in the everyday sense. They are precisely tuned mathematical relationships that allow for stability, complexity, and the emergence of observers capable of describing them. The entropy gradient required for memory and causality is extraordinarily special. The balance of forces that allows atoms, stars, chemistry, and life is finely constrained. Even if one rejects the language of design, the structure still demands interpretation. Because it is not just that something exists, it is that something exists in a way that is describable, stable, and mathematically coherent across scales ranging from quantum fluctuations to cosmic evolution. At this point, different philosophical paths diverge. One path says this structure is all there is, and its existence is ultimately unexplained. Another says the structure is part of a larger ensemble of possibilities, a multiverse in which all consistent frameworks exist, and we simply find ourselves in one compatible with observers. Another says the structure is the expression of deeper principles not yet understood, where information, geometry, and law emerge from something more fundamental still. And another path, the one we have been approaching indirectly throughout this series, asks whether structure itself is pointing beyond what structure alone can explain, not as an addition to physics, but as a question physics alone does not close. Because even if Platonia contains all possible configurations, even if time is emergent, even if information is the deepest language of description, the question remains suspended above all of it. Why is there any structure at all, instead of absolute nothingness? This is not a question about an event in time. It is not about a beginning. It is about the existence of the entire framework, in which beginnings and endings are defined, and it is here that the exploration reaches its quietest point. Not because the answer has been found, but because the tools of description themselves have reached their limit. We can describe how a universe behaves. We can describe how time emerges, how entropy increases, how observers form, how information organizes itself into memory and prediction. We can even describe, in increasingly sophisticated ways, what a universe would look like if time did not exist at all. But we cannot, within those same descriptions, fully account for why there is a describable structure in the first place. In the final chapter, we will gather the threads of everything we have explored: block universe, Platonia, time capsules, entropy, observers, and information. and we will return one last time to the experience that makes all of this unavoidable in the first place. The feeling that there is a present moment, the feeling that something is happening, and the question of what, if anything, that feeling is pointing to. After everything, after Platonia, after the Wheeler-DeWitt equation, after the Janus point, after entropy and information and the dissolution of time into structure, something remains that refuses to disappear: the present moment, not as a concept and not as a coordinate in space-time, but as an experience that seems to insist on itself more strongly than any theory that tries to explain it away. There is always, even when you understand all the arguments, a sense that something is happening now. Not in the abstract sense of now as a label, but in the immediate sense of being located inside a lived moment that feels irreducibly current. This is where the entire exploration circles back on itself, because every framework we have examined, in one way or another, attempts to remove the special status of the present. The block universe distributes all moments equally across space-time. Platonia removes time entirely and replaces it with static configurations. Quantum gravity eliminates time from the fundamental equation altogether. Thermodynamics replaces temporal flow with statistical gradients. Information theory replaces becoming with relations. Even consciousness, when analyzed physically, becomes a pattern embedded in structure. And yet none of these descriptions eliminates the fact that experience is always indexed to a single perspective. There is always a here, there is always a now, there is always a point from which the rest of the structure is encountered. Physics can describe correlations between events. It can describe how information is arranged. It can even describe how systems encode the appearance of flow. But the existence of a first-person perspective, a unified point of experience, remains something that is not obviously captured by the same language. Some interpret this as evidence that the present moment is an illusion generated by cognitive processes inside a static universe. On this view, the feeling of flow is simply what it is like for a self-referential information system to contain records, predictions, and internal updates. The brain constructs a model of change, and that model is experienced as passage. Others take a more cautious position. They suggest that while physics successfully removes time from its fundamental equations, it has not yet fully accounted for how those equations give rise to lived temporality. The absence of time in the formalism does not automatically translate into the absence of time in experience. It may indicate that our understanding of how experience emerges is incomplete, but there is a third perspective that quietly runs through everything we have explored. It is the idea that the present moment is not something to be eliminated, but something to be reinterpreted. In the block universe, the present is a slice of space-time indexed by a particular observer. In Platonia, the present is a configuration among all possible configurations. In the Janus point picture, the present is a position relative to a structure of increasing complexity. In information-based views, the present is a state of maximal integration of data within a system. In each case, now is not removed. It is relocated within a deeper structure. What changes is not whether the present exists, but what kind of thing it is. And this is where the tension between physics and experience becomes most visible. Because physics describes relationships without privileging any single point, but experience is always centered. It does not arrive as a map of the universe. It arrives as a point of view within it. The challenge, then, is not to deny one in favor of the other, but to understand how a centered perspective arises from a structure that, in its most fundamental description, does not contain centers at all. Some approaches suggest that this centering is a consequence of self-modeling systems. A brain is not just embedded in the universe, it contains a model of itself embedded in the universe. That recursive structure naturally produces a perspective that feels localized, unified, and continuous. The self is not an object in addition to the system. It is the system organizing information about itself in a particular way. From this perspective, The present moment is the point at which the system integrates information into a coherent model. It is not a boundary moving through time. It is the ongoing condition of being a system that models its own state. But even this explanation leaves something intact. It does not remove the fact that there is something it is like to be that system, and so we arrive at a subtle boundary in the entire discussion. Physics, in its most advanced form, has become extraordinarily successful at describing the structure of reality without reference to time as a fundamental ingredient. It has shown that many of the features we associate with temporal flow can be derived from deeper atemporal relations. It has revealed that memory, entropy, and causality can all be understood as emergent properties of more basic structures, but it has not eliminated the perspective from which those structures are experienced. Instead, it has relocated the mystery. The universe, as described by its deepest theories, is not a sequence of events unfolding in time. It is a vast, structured entity in which relationships encode what we interpret as change. Within that structure, certain configurations support observers. Those observers contain internal models that represent parts of the structure as past, present, and future. And within those models arises the sensation of being located at a moving point in time. Whether that sensation is fundamental or emergent remains an open question. But what is clear is that it is not easily dismissed, because even if every equation is timeless, even if every configuration already exists, even if every moment is equally real, the fact remains that there is always a perspective from which reality is encountered as present, and that perspective is where all questions begin. So we end where we began, but not in the same place. We began with the idea that time might not flow. We end with the recognition that even if time does not flow in the universe, something still flows in experience, or at least appears to. And the deepest question is no longer whether time exists in the equations. It is why the equations are ever experienced at all, not as structure, not as information, but as a moment, as this one. And now, as you step away from this exploration, the invitation is simple, not to resolve the tension, but to notice that it is still there. And if you enjoyed this slow descent through the deepest layers of time, structure, and existence, consider subscribing to Space Sleep Theory. There are still questions ahead that physics has not finished asking, and perhaps never will. For now, there is only this moment, and it is enough to end here